So that's why we divided by u1 with norm u1, that is 1 by 5 divided by root 3 by 5, that is equal to 1 by root 3. We have all three coordinates are 1 by 5, 1 by 5, 1 by 5, 1 by 5. Whenever you divide it by 1 by 5 by root 3 by 5, you will get 1 by root 3. Okay, so that's why first vector is 1 by root 3, 1 by root 3, 1 by root 3. The second vector u2 is equal to, what is our u2? u2 is minus 1 by 2, 1 by 2, 0. We divided by minus 1 by 2, 1 by 2, 0 divided by 1 by root 2. So that will become minus 1 by root 2, 1 by root 2, 0. Okay, and now u3 divided by norm u3, that will become 1 by root 6, 1 by root 6 minus 2 by root 6. Okay, so here is the answer our that required orthonormal set is given by u1 upon norm u1, u2 upon norm u2, u3 upon norm u3, that is equal to 1 by root 3, 1 by root 3, 1 by root 3. Second vector is minus 1 by root 2, 1 by root 2, 0, and the third vector is 1 by root 6, 1 by root 6 minus 2 by root 6. So next question, question number 5b, first part. Find the basis for the orthogonal complement of the subspace W of R3 defined as W is equal to x, y, z belongs to R3, where minus 2x plus 5y minus z is equal to 0. Here is this question asked in 3 marks. Here is the solution. Here we have minus 2x plus 5y minus z is equal to 0. So we convert that solution, that W, into the matrix. Okay, so let you can see second and third column does not have leading entry. So let take y is equal to k and z is equal to t. So you will get x is equal to 5k minus t divided by 2. So hence the basis vector for W. Here we want to find first of all basis vector for W. Okay, so whenever we take y is equal to k, z is equal to t, we will get x is equal to 5k minus t divided by 2. So hence basis vector for W are W1, that is the coefficient of k in x, y, z. The first vector W1 is exactly the coefficient of k in x, y and z. So in x coefficient of k is 5 by 2, so 5 by 2. In y coefficient of k is 1, so 1, and in z coefficient of k is 0, so 5 by 2, 1, 0. Similarly, W2 is exactly the coefficient of t in x, y and z. So the coefficient of t is minus 1 by 2. The coefficient of t in y, that is 0, and the coefficient of t in z, that is 1. So minus 1 by 2, 0, 1. The space W spanned by the W1, W2 is the same as the row space of the matrix A. That you should know. The space W spanned by the vectors W1 and W2 is exactly the same as the row space of the matrix A, 5 by 2, 1, 0. This column vector we convert into a row vector, 5 by 2, 1, 0, minus 1 by 2, 0, 1, 5 by 2, 1, 0, minus 1 by 2, 0, 1. Okay, so by now what we have to find, we want to find orthogonal matrix of the W. Okay, what is our question? Just find a basis for the orthogonal complement of the subspace W. Okay, and for that we use this theorem. By known theorem, the null space of A is the orthogonal complement of W. The null space of A is the orthogonal complement of W. So to find the null space of A, we convert this matrix into a row echelon form. So that's why we multiply first row with 1 by 5 and add into the second row. So first row is as it is, 5 by 2, 1, 0. So the second row become 0, 1 by 5 1. Okay, so now this matrix is in row echelon form, correct, because first row have leading entry, below that leading entry we have 0, and the second row have leading entry, and below that leading entry there is no element, right? So this matrix is in row echelon form. So using that row, now to find null space of the given matrix, we convert this matrix into the equation 5 by 2 x plus y is equal to 0 and z is equal to 0. Okay. Okay. Now second row we multiply, here we multiply second row with minus 1 by 5. We multiply first row with minus 1 by 5 and add into the second row. So that matrix become 5 by 2 1 0 0 0 1. So this is the row echelon form. So 5 by 2 x plus y is equal to 0 and z is equal to 0. So take y is equal to k. Take y is equal to k and x is equal to minus 2k by 5. So basis for the orthogonal complement of w is minus 2 by 5 1 0. Okay, minus 2 by 5 1 0. So here is a complete this question, and let's see question number 5b, second part. This question asks in 3 marks. Find the matrix P that diagonalizes this matrix A 1 0 minus 1 2, and hence find A raised to 13. We want to find A raised to 13. So this question is a chapter of eigenvalue and eigenvector, from chapter of eigenvalue and eigenvector. So first of all we want to find the characteristic. In fact if you know that one theorem, that in triangular matrix the eigenvalues are exactly the main principal diagonal elements of main principal diagonal. So here this matrix is in lower triangular matrix 1 0 minus 1 2 2 cross 2 matrix, but this matrix is in is a lower triangular matrix, right? And any triangular matrix, either it's lower triangular matrix or upper triangular matrix, the main principal diagonal elements are exactly the eigenvalues of the given matrix. If you know that theorem, you can easily understand that 1 and 2 are the eigenvalues of the given matrix. Okay, you don't need to find actually. Otherwise by the method you can solve. The characteristic equation of A is A minus lambda I, determinant of A minus lambda is equal to 0, and determinant of A minus lambda I, that is 1 minus lambda 0 minus 1 2 minus lambda is equal to 0. Solving this determinant you will get lambda is 1 and lambda is 2. Okay. So 1 and 2 are eigenvalues. Let x1 x2 be the eigenvector of a corresponding to the eigenvalue. Now we want to find the eigenvector corresponding to lambda is equal to 1 and 2. Okay, corresponding to lambda is equal to 1 and 2. So let x1 x2 be the eigenvector of a corresponding to the eigenvalue lambda 1 is equal to 1. The matrix equation A minus lambda 1 I into x1 equal to 0. So put lambda 1 is equal to 1 in the given determinant. 0 0 minus 1 1 0 0 minus 1 1 into x1 x2, that is equal to 0 0, which gives minus x1 plus x2 is equal to 0. So let x2 is equal to k, x1 is equal to k, and hence if we take k is equal to 1, 1 1 is the eigenvector corresponding to lambda is equal to 1. Okay. Let x2 is equal to y1 y2 be the eigenvector corresponding to the eigenvalue lambda 2 is equal to 2. The matrix equation A minus lambda 2 I into x2 is equal to 0 gives minus 1 0 minus 1 0 y1 y2 equal to 0 0, which gives y1 is equal to 0, but about y2 we don't have anything, so take y2 is equal to k. So hence 0 1 is the eigenvector corresponding to lambda 2 is equal to 2. So what is our P? Corresponding to lambda is equal to 1, we have eigenvector 1 1, and corresponding to lambda is equal to 2, we have eigenvector 0 1. So put that 2 eigenvector into the column, into the columns of column in P. So that's why the first column of P is corresponding to lambda is equal to 1. Eigenvector of corresponding to lambda is equal to 1 is 1 1. So the first column of the matrix P is 1 1, and corresponding to lambda 2 is equal eigenvector corresponding to lambda 2 is equal to 2 is 0 1. So the second column of the matrix P is 0 1. Okay, and hence P inverse. Now for 2 cross 2 matrix, to find inverse of the matrix is quite easy. Okay, just adjoint of the matrix upon determinant of A. You can see determinant of that matrix is 1 1 into 1 1 minus 1 into 0 0. So 1 minus 0, that is 1. Okay, so adjoint of A, sorry, adjoint of P is equal to exactly the inverse of the matrix. So to find in 2 cross 2 matrix, to find inverse of the matrix is quite easy. Adjoint of the matrix upon determinant of A, here determinant is 1, so inverse of that matrix is exactly the adjoint of the given matrix. Okay, and that matrix, if you want to find that matrix, we interchange the main principal diagonal elements, but in main principal diagonal elements we already 1 1. So whenever we interchange, that will become same 1 1, and just sign, we have to just change the sign of the another diagonal elements. So another diagonal elements are 0 1. So whenever we changing the sign, 0 become 0, but 1 become minus 1. So that's why P inverse is equal to 1 0 minus 1 1. Now D, capital D is equal to P inverse AP. So P inverse AP, that is P inverse is 1 0 minus 1 1, A is 1 0 minus 1 2, and P is equal to 1 0 1 1. Whenever we multiply this 2 cross 2 matrices, we will get D is equal to 1 0 0 2, exactly the triangular matrix which have main diagonal elements are 1 and 2, that is exactly the eigenvalues. And now we want to find A raised to 13. For A raised to K, we have the formula that P D raised to K P inverse. So that is 1 0 1 1, D raised to 13, that is equal to just we 1 raised to 13 0 0, 2 raised to 13 1 0 minus 1 1. So that is equal to 1 0 1 1 into 1 0 0 2 raised to 13, that is 8192 8192 1 0 minus 1 1. So whenever we multiply this 3 matrices of 2 cross 2, we will get 1 0 minus 8191 and 8192. So here is the answer, A raised to 13 is equal to 1 0 minus 8191 and 8192. So up to this question, after 5 minutes we will take another questions, right? So